In two other separate videos, we demonstrated how to configure PETSc using GNU and Intel compilers, respectively. Today we are going to demonstrate how to configure and build PETSc with CUDA toolkit to enable the GPU accelerated scientific computing capability. By integrating these two, we can dramatically reduce computation time for demanding simulations, improve scalability across nodes, and make our codes more energy efficient. Nowadays, when we talk about the scientific computation of linear algebra in GPU, we usually have two options. Either you would like to do it in the CUDA ecosystem in NVIDIA scientific graphic cards, or you are enthusiastic about adopting the ROCm ecosystem in AMD graphic cards. There are pros and cons on both sides. For instance, CUDA ecosystem is very mature, efficient, well managed over versions, and widely accepted in diverse communities. You are able to find numbers of cases to learn and explore. In terms of the implementation in PETSc, CUDA toolkit is natively integrated in PETSc packages, which can be directly called inside the PETSc program. Since we are focusing on solving large-scale linear algebra systems, the related CUBLAS, CUSparse, CUSolver libraries have been super mature over the years. In fact, you do not need the very recent CUDA versions to gain the superb efficiency on solving linear algebra system in GPU, which you might consider as an advantage. However, the downside of CUDA is that it is limited to NVIDIA graphic card, and which is usually much more expensive than their AMD counterparts at the similar computing power. At this point, you might consider AMD graphic card as your optimized decision. However, ROCm ecosystem is much less mature than CUDA and has significantly fewer real-world cases you can learn from, compared with CUDA. Not to mention that the strong and stringent constraint on matching versions between ROCm, operating system, drivers, and dependent packages. In practice, you have to lock down the versions of your driver, operating system, and ROCm and avoid upgrading them over years so that you can run your ROCm code stably. In terms of numerical algorithms, the PETSc works on AMD GPUs via the HIP interface, the heterogeneous computing interface for portability. The preconditioners in ROCm are relatively less developed compared with CUDA, so usually you will rely on GPU-enabled hyperpackages to offer the choice of preconditioners. Nonetheless, it is also noteworthy that the scientific computing AMD graphic cards are usually hard to find in the market, unless purchased by the large enterprise or company. You might need to consider these factors if you have a long-term plan for your project. Firstly, let's look at how to prepare our operating systems before installing PETSc with CUDA toolkit. As usual, we assume you are using Ubuntu 24.04 operating system. There are a number of packages you need to on Ubuntu before installing PETSc. For instance, Build Essential, Fortran, Git, Python, OpenBLAS, libnuma, and so on. After installing these packages, you are also suggested to install multiple versions of GNU compilers if you have to work on some legacy codes and C++ projects. Now, we have to ensure that the NVIDIA driver and CUDA toolkit are ready for our PETSc package. To get this done, you have to pick the right versions of the NVIDIA driver and CUDA toolkit. The versions should not be too old or too new, since you need to consider the compatibility on the hardware level between the GPU and driver, and also the compatibility on software level between the driver, CUDA toolkit, and PETSc software. Generally, if you install an NVIDIA driver that is greater than 535 to 570, CUDA toolkit between 11.8 to 12.5, your installation should be okay for the latest version of PETSc and the majority of the concurrent scientific computing NVIDIA graphic cards. In this video, we are going to install NVIDIA driver 570, CUDA 12.5, and PETSc 3.2.3.5. Before installing anything, you should remove any old installation of NVIDIA drivers and update your Ubuntu repositories. Then, you can download the deb file of NVIDIA driver 570, save it in your home directory, and follow the steps on this page to complete the installation. Eventually, you may verify your installation by typing NVIDIA SME to check its version. Here, we would like to highlight that if you are working on HPC or headless server system, we highly recommend you to install NVIDIA driver using deb file instead of .run file. This is not only because the deb file approach makes installation, update, maintenance easier, but also it automatically installs the required packages and matches kernel headers, which can be a headache on headless server system. After installing the NVIDIA driver, we can start installing the CUDA Toolkit 12.5. Foremost, we remove any old installation of the CUDA Toolkit. Then we add the CUDA repository to your system and download the specific version of the CUDA Toolkit for Ubuntu 24.04. After everything is done, we can install the CUDA Toolkit without the NVIDIA driver, since you have done so previously. After that, you add the installed CUDA libraries to the search path of your operating system, so the other external packages like Hyper and PETSc can find it. Here we also suggest installing the CUDA Toolkit via .deb file instead of run file, unless you would like to install multiple versions of CUDA altogether. In general, we do not want to fix the deb file and .run file approach together for the NVIDIA driver and CUDA Toolkit. After you have installed NVIDIA driver and CUDA Toolkit, you are highly recommended to install GRCOPY package. GDR copy is important for CUDA and PETSc because it optimizes GPU, CPU communication, which is often a bottleneck in distributed GPU computing, especially when PETSc is used in MPI-based HPC environments. First of all, we enter the user's home directory, push the GitHub repository of latest GRCOPY to the local host, and make a folder called GRCOPY_binary to store the installed binary files. Once we are inside the local workplace of GRCOPY repository, we type make all together with prefix flag to configure our GRCOPY package. Following that, we type make install together with prefix flag to install the GRCOPY on your operating system. It should be noted that make install command should be executed using super user permission. After installation, we can type sudo /insmod.sh and sudo config to refresh the dynamic links. Besides GRCOPY package, which we use for ultra-low latency GPU-CPU memory copy, the UCX package, a high-performance communication framework for MPI, is also very important to CUDA and PETSc. Before installing the UCX package with GRCOPY enabled, you should use Ubuntu repository to install some package libraries. For example, libshaccess, package config, libudev, libtool, and so on. After that, we enter the user's home directory, create a folder called UCX_CUDA to store the binary files, download the latest UCX package, and extract it. Once we are inside the root directory of UCX, we type /autogen.sh and key in the configure flags to link UCX with GRCOPY and install its binary files into that specific folder using the prefix flag. You are also required to type make and make install. After finishing all these steps, add the following lines into .bashrc file and source the .bashrc file so the other external packages can find it. Eventually, you may use the two commands below to verify your installation too. Besides GRCOPY and UCX packages, HOLOC, the hardware locality library, is also an important library to give MPI and UCX precise hardware topology awareness, which is critical for binding CPU threads and GPU to minimize latency and maximize bandwidth. To install HOLOC library, we first enter the user's home directory, create the folder called HOLOC_binary to store its binary files, download the latest HOLOC tarball, and extract. Once we are inside the source codes, we type configure with the prefix flag, and followed by make and make install. We also subsequently add the installed HOLOC libraries into the searching paths in our operating system and source the bashrc file. Now, we can install the GPU-aware MPI so that the MPI libraries can eliminate the GPU-CPU memory copy bottleneck during communication. It can detect when a pointer is in GPU memory and uses optimized transport, like UCX package, instead of forcing the programmer to copy to host memory first. To install it, we first enter the user's home directory, create a folder called openp_CUDA, download the tarball, and extract. Once we are inside the root directory of openp, we type configure together with its configuration flags. After installation, include the installed MPI libraries into the searching path of the operating system and source the bashrc file. After installing GRCOPY, UCX, HOLOC, and openp packages, we can start installing GPU-enabled Hyper package. Similar to the other packages, we enter the user's home directory, create a folder called hyper_CUDA, and pull the GitHub repository of the latest Hyper to the local host. Once we enter the src folder inside the root directory of Hyper, we type configure together with the configuration flags as shown here. Besides specifying all the paths of external libraries correctly, you are required to take note the correct architecture of GPU and include it in the configuration flag. For example, RTX 5090, RTX 4090, and V100 are SM_120, SM_89, and SM_70 respectively. After finishing all these steps, you can include the installed binary files of GPU-enabled Hyper into the searching paths in .bashrc file and source it. After all these preparation, similar to the installation of the other packages, we enter the user's home directory, create a folder called PETSc_CUDA, download the tarball of latest PETSc, and extract. We enter the root directory of PETSc and start our configuration with the configuration flags as shown below. All these external packages in the configuration flags are recommended for the installation of PETSc. You should pay attention and specify the GPU architecture in your configuration flag. After installation, remember to include the installed PETSc binary files into the searching path of your operating system in bashrc file and source. Now, you have a clean installation of GPU-enabled PETSc for your project.